Hello, I welcome you all in this presentation related with the subject materials processing, fundamentals and practical. And we are talking about the welding of metals. In this particular presentation, there will be two types of the process which will be covered. One is the tungsten inert gas welding, also known as gas tungsten arc welding GTAW. Okay, and another is the plasma arc welding. So the two processes to a great extent have a lot of similarities, but there are a lot of dissimilarities also. So that is why these two processes are used in different domains. Okay. So these the tungsten inert gas welding and plasma arc welding. So as far as the similarity is concerned in these two processes, our electrode is same, no, in both these processes like TIG and the plasma arc welding. So electrode is tungsten electrode is used in both these processes, and it can be coated electrode. Okay. So coating of zirconium or thorium, that is used particularly for increasing the life of electrode, no, a tungsten electrode. If we use bare electrode, uncoated electrode, then the life is little limited, and then it also increases the current carrying capacity of the electrode. Like say for example, if the for a given diameter of tungsten electrode, if the current carrying capacity is 120 ampere, maybe by coating the electrode, the current carrying capacity can be increased to 150, 160 for the same life, because if the coating is not done, then thermal degradation is fast. So this is one, and this type of electrode is used with both these processes. Okay. And see, in these processes, since our electrode is of tungsten, so this is not consumed, electrode is not consumed in both these processes. So both these processes use non consumable electrode. But if we have to use the filler metal due to any reason, say adjusting the weld metal composition or thickness is too high and the edges have been prepared, so for filling the gap also we need to use the filler metal. So the filler wire can be used separately, but that has to be fed. So say this is the arc zone, we have to feed the filler wire separately. So we can use the suitable wire feeder, and that will be feeding the filler wire in the weld pool. Okay, say this is the weld pool, this is the arc, okay, and this is the base metal. So here in the pool our wire will be fed. So on dipping, so there will two things that will be happening. As soon as the filler wire enters in the arc zone, heating will start and also it will melt, but for smoother transfer we may dip partially in the weld pool, so that the molten metal from the filler wire is transferred to the weld pool smoothly. So as I said, there can be two purposes. One is like to adjust the weld metal composition suitably, so that we get the desired structure properties, as well as the solidification temperature range is enhanced, so the cracking tendency is avoided. So that is one purpose. So to realize the desired set of properties and avoid the cracking tendency. Another purpose, when the thickness is more, so the edges have been prepared. So when the edges have been prepared, we need to fill this gap or the groove by using the suitable filler. So to fill the gap, you can say we have to use the filler metal separately, and this is true in case of both processes, like in tungsten inert gas welding and the plasma arc welding. Now, as far as the differences are concerned, like say in the differences, like here another similarity is like the plasma is produced in both the cases, but very weak plasma is produced in case of the TIG welding, and very intense and powerful plasma is produced in case of the plasma arc welding process. Okay. So this is about the similarity part. Now we will see the differences. So the one major difference is the you see, in one case the arc is the main source of heat, while the plasma is used as another major source in case of the plasma arc welding for source of heat. So what happens in arc TIG welding, You see, in case of the TIG welding, arc is very thin and very weak, okay, because it is developed using the low current. On the other hand, arc is in plasma arc welding, arc is primarily used to ionize the plasma forming gases, and those the plasma gases are then passed through the constriction nozzle, where constriction of the plasma takes place, that in turn helps to increase the power density associated with the plasma. So, here it is the normal arc, okay, which is used to generate the heat based on the VI principle, but in case of the plasma, arc is primarily used to ionize the plasma forming gas and to produce the plasma. That plasma is later on passed through the nozzle to facilitate the constriction. So, in plasma we use the constricted arc plasma, and this constriction means if our arc is like this, then the plasma will be passing through the very narrow nozzle of the smaller diameter, and so the plasma forming gas will be and plasma will be passed through the nozzle at very high speed. Okay. So, this in turn increases the power density associated with the plasma arc welding. This also helps in increasing the temperature realized by the plasma. Okay. So, in case of the TIG, and in case of the plasma, we use simply arc, and here we use the plasma. Okay. So, here basically the temperature is low, and because of the constriction in the plasma, the temperature is significantly high, which may be like 15,000, 20,000 degree centigrade, as compared to the TIG arc, which may be like 5,000, 6,000, 10 or 10,000 degree centigrade, depending upon the current conditions being used. And there is no constriction in case of the TIG, but in case of the plasma, constriction is used. Okay. So, because of the high temperature and high velocity plasma, the plasma is also used for the cutting applications. Okay. So, if we compare the since the power density associated with the TIG and the plasma, these are the two significantly different in case of the TIG and the plasma. Therefore, the net heat input that is required for the welding purpose in case of the TIG is higher, and for the plasma, net heat input required for welding the given metal of a given thickness is lower. Okay. So, these differences actually lead to the significant difference in the performance and the capabilities of the two process. The TIG being the low heat input process, relatively low heat input process as compared to the other arc welding, not with the plasma welding. So, the TIG is basically the slow process, while the welding can be done using the plasma at higher speeds. Okay. So, this is about the differences. Now, we will talk a little bit more about the various technological aspects associated with these two welding processes. So, as I said, so both these processes use the DC, direct current welding power source, DC power source. Okay. And invariably DC SP, DC is, current straight polarity is used, means the electrode is connected to the negative terminal and workpiece is connected to the positive terminal. Okay. So, this helps in generating more heat on the workpiece side, because when the DC is used, 2/3 of the heat is generally generated on the workpiece side and on the anode side, and the 1/3 of the heat is generated on the cathode side. So, if we are using the DC SP, then lesser heat will be generated on the electrode side and more heat will be generated on the workpiece side. So, this kind of the polarity helps in reduced heating of the tungsten electrode and more heating of the workpiece side. So, this kind of the polarity therefore helps in increasing the life of the tungsten electrode, and this is generally used with both the TIG welding and the plasma arc welding. Okay, while welding the steels. But if we are dealing with the non-ferrous metals, then the reverse polarity is used, and when we use the reverse polarity means electrode is positive. So, say for welding of the non-ferrous metals, okay, where metal forms the oxides rapidly due to the interaction with the atmospheric gases. So, in order to have the better cleaning action, the DCRP is used. When the DCRP is used, then means our electrode is connected to the positive terminal and the workpiece is connected to the negative terminal. So, in this approach, although this helps in realizing the better cleaning action, especially in case of the non-ferrous metals, because of the mobile cathode spot formation on the workpiece side. Okay. So, this helps in loosening the oxide which is being formed on the surface of the weld pool, and that helps in better cleaning action as compared to the DCSP. Okay. But the problem is the more heat generated on the electrode side causes the greater thermal damage to the electrode. Because of the more heat generation, greater thermal damage that will be experienced by the electrode. So, the life experienced by the electrode in the DC, in case of the DCRP, that is lesser. So, the DCRP adversely affects the life of the electrode, and we need frequently replace or resharpen the electrode when the DCRP is used. Okay. So, as far as the so here we have the power source, say electrode is connected to the negative terminal, we can see here tungsten electrode, and the positive terminal is connected to the workpiece. So, this is the kind of the DCSP straight polarity. Okay. And the power will be delivered to the electrode, and this electrode will be mounted in the contact tube. This is a welding torch. Welding torch will be fed with the shielding gas. This shielding gas is usually either helium or it is argon. We do not use the CO2. Okay. So, this shielding gas will be passing through the nozzle, and then after coming out of the nozzle, it will be forming very firm cover around the welding arc and pool. So, basically the jet of the inert gas that comes out of the nozzle forms very firm cover around the arc and the weld pool. So, when this firm cover of inert gas is formed, this provides the effective protection to the weld pool. So, the protection in GTAW of the weld pool is really good, and therefore, we get very good, very reduced percentage of the oxygen and nitrogen in the weld pool, and that in turn helps in producing the cleanest weld metal by the GTAW process amongst the arc welding processes. Okay. So, this is about the electrode, and sometimes when the if the current if the welding power source is of the lower rating and the welding torch is of the lower rating, means it can handle say up to 200, 150 to 200 ampere current or even lesser. So, when the low current is used, even air cooling helps in maintaining the temperature of electrode within the safe limit. So, we can use the air cooled welding torches, and but if we are using the higher current, then higher current causes the electrical resistance heating of the electrode apart from the heating of the electrode from the arc. Okay. So, to maintain the temperature of the electrode within the safe limits, water cooling is used. Okay. So, for higher capacity, higher current rating welding power sources and welding torches, we need to use the cooling system, water cooling. So, here the water will be fed from one side and it will be taken out from the other side for cooling purpose. Okay. So, the electrode strikes the arc with the base metal. Once the arc is established, melting of the fin surfaces will be taking place. Okay, and part of the heat that will be dissipated to the underlying base metal will be producing the heat affected zone on both the sides. So, this approach is same. There are two aspects. One is the arc length that is used in the TIG welding is very short. It is like say 2 to 5 mm. Okay, and we use the inert gases as the shielding gas, inert gases as shielding gas. So, these two aspects help in producing very clean weld metal. Apart from that, the very stable arc is also produced by the tungsten electrode. Okay. So, this is about the setup. So, as far as the process parameter is concerned, usually very low current like say 20 to 50 ampere to like say the 200 or even 300 ampere welding current can be used. So, depending upon the current rating, the different types of the power sources and torches are available. The voltage, arc voltage used is very less, like say maybe 10 to 20 volt at the it is around mostly 12 to 15 volt. So, depending on the type of the electrode and its diameter, we use suitable arc voltage and the suitable welding current. So, the welding current, as I have already talked, depending upon the net heat input required for the welding purpose, we use current and we use the speed, so that the desired net heat input is realized for welding the given workpiece metal. So, the metal, its thermal conductivity and section thickness, these two things will decide how much net heat input is to be used for the welding purpose. Okay. So, now the speed certainly can be used as per our convenience, like 50 to 200 or 120 per minute. So, speed, we increase the, if we increase the speed, then our net heat input will be reduced. If we reduce the speed, heat input will be high, because H net depends simply on the V I by S for a given thermal efficiency. So, increasing the speed will reduce the net heat input, increasing the welding current will increase the net heat input. So, these two V and I are used for adjusting the net heat input to be supplied during the welding. About the polarity, I have already asked. Mostly for the ferrous metals we use the DCSP, and for the non-ferrous metals we go for the DCRP. Okay. The net heat input we can calculate, although this is a low heat input process, maybe like say 0.4 to 1.5 kilojoule per mm net heat input, but this will again depend upon the type of metal, its thermal conductivity and the section thickness. Okay, as I have already said, protection to the weld pool in the GTAW welding process is very effective, because it uses the short arc length, the arc is very stable, and the inert gases are used for the shielding purpose. So, these three factors in combination produce the very effective, provide the very effective weld pool protection, and that helps in maintaining the very good quality of the weld metal produced. The welding power source is concerned, mostly we use the DC power source but we can use the AC also for the non-ferrous metals. And so, the AC and DC both can be used, but the AC is primarily used for the non-ferrous metals and DC is used for the ferrous metals. If we have to use the DC with the non-ferrous metals, then this is the DC RP that will be used, as I have already talked. Okay. Now, coming to the weld metal and heat affected zone properties. So, as compared to the SMAW, SAW, GMAW, as compared to these processes, the GW or the TIG welding, this is a low heat input process, low net heat input process. So, because of this low heat input, the weld cross section that is produced is very small. So, we get our weld cross section area is very less. So, this less weld cross sectional area reduces the issues related with the residual stresses and the distortion related. Okay. This is one aspect. The second is the amount of heat is because of heat input is very less. So, the amount, since we are supplying very less heat, so the heat dissipated to the underlying base metal is also less, and therefore, the zone which is affected by the heat away from the fusion boundary, that is also very narrow, and this in turn leads to the narrow heat affected zone with the TIG welding. Okay. So, this is the narrow heat affected zone and the very small weld bead cross section. Okay. Another interesting aspect here is what, like since the weld is developed using very low heat input. So, when our heat input is low, cooling rate is found inversely proportional to the net heat input. If heat input is very low, then our cooling rate will be very high. So, high cooling rate leads to the various aspects, like higher cooling rate may be desirable, may be undesirable, depending on the kind of metal system which is there in. So, if the cooling rate is high, certainly it will be producing the fine grained structure, but it will also be reducing the time for solidification, means the gas and inclusion entrapment tendency will be increased. Okay. So, the tendency of this entrapment will increase, means if the gases and inclusions are there, then that tendency will increase, although with the GTAW this possibility is very less. Now, higher cooling rate on the other hand, in case of the transformation hardening metals, will tend to produce the martensite, and that can lead to the embrittlement and cracking tendency. So, and this is primarily attributed to the higher cooling rate. Okay. So, on the other hand, if you are dealing with the non-ferrous metals where transformation hardening is not very effective, then what we may find that the grain refinement may result in the better properties as compared to the base metal and the heat affected zone. For example, if our the base metal is very coarse grain, it is produced say by casting, and now the weld joint is to be made, okay, like this. So, the since coarse we have very coarse grain structure in the base metal produced by the casting, when this is welded, this will be producing extremely fine dendritic grain structure. Okay. So, this in turn can result in the weld's property variation in terms of the hardness like this. Base metal is less, but the weld zone is very high. Okay. And this is attributed to the fine grain structure that will be produced. This is particularly true in case of the cast metals. Okay. But if it is the steel, then certainly due to the transformation hardening, or the weld zone will be and heat affected zone will be showing significant increase in hardness as compared to the base metal. So, this is attributed to the martensitic transformation in the weld and a little partial martensitic transformation in the heat affected zone. So, depending upon the kind of metal systems, response to the mechanical properties of the weld joint, mechanical properties of weld joint will heavily depend upon the kind of metal systems and its metal strengthening mechanism. Okay. Now, as far as the application is concerned, GTAW is used for both thin and thick sections. So, certainly, so it up to like say a single pass through thickness penetration can be realized up to 3 mm using the GTAW. Okay. So, for welding thin sheets using low current, this is very effective because it is a low heat input process. But if you have to produce a quality weld, okay, for critical applications, then edges need to be prepared, groups need to be prepared, and those will be filled in gradually by using the number of passes, okay, using very low heat. So, each pass will be producing very small size bead with the help of low heat, and then but it will be taking large number of passes. So, our productivity will be reduced, it will take long time to produce and complete large number of passes to produce a weld joint. Okay. So, the multi-pass GTAW is preferred when the quality welds are used, say for the nuclear applications or very critical weld joints used in the pressure vessels and likewise other components. Okay. This is the application wise. So, the quality of the weld joint produced by the GTAW is extremely good. That is why it is used for critical applications. Why? Because if it is thin, then if it is a thin section welding, then it produces very small weld and very narrow heat affected zone, reduced residual stresses and distortion tendency. Okay. And our the reduced the oxygen and nitrogen content in the weld metal, so reduced the tendency of forming the defect in the weld joint. So, these are very good aspects associated with the welding, and this happens primarily due to the net heat input, reduce a very less heat input which is used for development of the weld joint by the GTAW process. Okay. So, now we will be talking about the plasma arc welding. In case of the plasma arc welding, it has, as I have already said, it has a lot of similarities, but few dissimilarities also. Like in TIG, we use only shielding gas like argon or helium, but in plasma we use the separate plasma forming gas. Okay. And as I have said earlier, there is no constriction in the TIG welding, but there is a constriction of the plasma in case of the plasma arc welding. Okay. So, depending upon the kind of the current rating, the plasma arc welding is used in 3 ways, or it is categorized in 3 ways. One is the microplasma. So, it produces very thin and very weak plasma, particularly suitable for thin sheet welding. Okay. So, this is produced using the current of less than 15 ampere. And in another is the the plasma where the melt in mode is used. This uses the current of 15 to say 400 ampere. So, what is this? In melt in mode, what we do, we just try to melt the fairing surfaces and allow it to solidify, and this is particularly suitable for again thin sheet welding. So, microplasma is about the less low current plasma, but in case of the melt in mode plasma arc welding, the weld joint is produced simply by the melting and the solidification of the weld pool. Okay. So, this is another approach. This is also used for the thin sheet welding. Okay. The plasma is not strong and it is weak, but when we use a keyhole mode is particularly used, it uses a high current plasma and it is used for welding of thick sections. So, what is this? The keyholing. So, when we use the high current plasma, so how it works? So, let us talk about that. So, we use the DC power source, which is again using the DC SP tungsten, and the negative terminal is connected to the tungsten electrode. Then arc can be striked between the electrode and the nozzle, or it can be striked between the electrode and the base metal. Okay. So, we have electrode like this and we have nozzle. So, we can strike the arc between the electrode of tungsten and the nozzle. Then our plasma forming gas will be passed through the will be passed through the arc. So, when the plasma forming gas passes through arc, it gets ionized. Okay. So, this ionized gas will be termed as plasma. This ionized gas later on then passed through the constricted nozzle of the constricted nozzle is a very small diameter. Nozzle will have opening of very small diameter through which the plasma will be forced to pass through. When the plasma passes through the nozzle, it gets constricted, means its diameter is reduced and passes through the nozzle at very high velocity. So, the two things will happen: reduction in cross section, smaller cross section, and increased speed. Okay. Reduction in cross section of the plasma and increased speed of the plasma. When these two things happen, the power density is enhanced significantly in the plasma, and that increased power density helps in fast melting of the fairing surfaces of the base metal, and that in turn will be reducing the reduced heat input required for the welding purpose. So, increased power density due to the constriction and increased speed of the plasma, or the H net required is reduced, and the reduced H net increases the cooling rate. Okay. This is just one aspect. Second aspect is like when like say these are the edges, and when the plasma, a high velocity plasma is being used, it melts thin zone. Okay. Because of the high power density at the center, the metal gets evaporated, and this in turn produces the hole. Okay. So, metal evaporation builds up the pressure in the molten metal. So, say this is the molten pool. Okay, and at the center where power density is maximum. So, what it will be causing, the vapor zone is produced in form of like the simple shaft or the pipe made of the vapor is produced, and this vapor causes the internal pressure on the molten metal, okay, for maintaining its stability. So, if our the speed, heat, the current density associated with the plasma, if these three are maintained properly, then this hole, okay, which remains stable due to the internal vapor pressure, and all around this we have the molten pool. This hole is known as keyhole. This keyhole this keyhole helps in delivering the heat up to the root of the parent metal. which is being welded. And because of this, the keyholing approach allows the welding of the thick sections also. So, we can see here, this is the tungsten electrode which is connected to the negative terminal, positive terminal is connected to the base metal, arc is striked, this is the arc, and then we will be feeding the plasma forming gas. Plasma forming gas will be passed to the arc. So, there it will get ionized and produce the plasma. Then this will be constricted. Okay. When it is constricted, is the cylindrical shape, the plasma jet will be coming out, which is constricted, very intense in terms of the temperature, and then this will be feeding, supplying the heat. So, here the weld pool will be produced, and at the center in keyhole approach, when the current is high and proper the welding speed, the current density, plasma velocity, when all these three are maintained, we get the very stable keyhole. So, that allows the delivery of the heat up to the root, and that in turn permits the welding of the thick sheets very effectively. Okay. So, if any of these like current, the power density and the speed of the welding and the velocity of the plasma, if any of these are disturbed, then keyhole gets collapsed. Okay. And then our welding will become unstable, right. So, in melt in mode, there is no keyhole, simply melting and melting of the fixed surfaces followed by solidification, the joint will be developed. So, about all these things I have already talked. We use the tungsten electrode, it can be coated, we choose the suitable kind of the welding current as per the kind of plasma to be used, whether for melt in mode, micro plasma or keyhole mode. Polarity is certainly DC or SP is used, heat input is selected as per the need and purpose, a section thickness which is to be produced. Just like GTAW, protection is very good because it also uses the argon or helium gas, then power source is the DC, and the weld metal and HZ properties, maybe our weld cross section or weld cross section is further smaller and HZ is further finer because of the higher power density associated with this plasma arc welding and the lesser heat input. Okay. And the application and the thickness and other things are like say the plasma can be used for thin using the microplasma, and for very thick sections if you are using the keyhole approach. Quality is very good, and it can be used for welding the metals which are sensitive to the atmospheric gases, otherwise it will be a costly affair. And also or the helium is used as a shielding gas. So, the plasma has got lot of similarities with the TIG, but lot of dissimilarities also, that makes it very unique. Okay. Now, I will summarize this presentation. In this presentation, basically I have talked about the two arc welding processes, one is the GTAW and another is plasma arc welding. GTAW is primarily used for thin section welding, and the plasma can be used for the both thin and thick sections. Thank you for your attention.